Good morning, champs. Today we take our first real calculation in boundary layer theory. In the previous video, we introduced the idea of a boundary layer. We saw that because of viscosity and the no-slip condition, the fluid velocity changes from zero at the wall to the freestream velocity within a thin region of thickness delta. Now, instead of solving the full boundary layer equations, we start with a very simple model for the velocity profile. We assume that inside the boundary layer, the velocity varies linearly with y. So we write u over u infinity equals y over delta. Or, equivalently, u equals u infinity times y divided by delta. This means the velocity is zero at the wall and increases linearly until it reaches the free stream velocity at the edge of the boundary layer. Before using this model, let us check the boundary conditions. At the wall, y equals 0. Then the velocity becomes u equals 0. So the no-slip condition is satisfied. At the edge of the boundary layer, y equals delta. Then we get u equals u infinity. So the model also matches the free stream velocity. That is good. Even though this profile is simple, it satisfies the two most important physical conditions. Now let us compute the velocity gradient in the y direction. We differentiate u with respect to y. Since u infinity and delta are constants with respect to y, we obtain partial u over partial y equals u infinity divided by delta. This is an important result. The velocity gradient is constant across the whole boundary layer in this simple model. Now we use Newton's law of viscosity. The shear stress is given by eta times partial u over partial y. So we get tau equals eta times u infinity divided by delta. At the wall, this becomes the wall shear stress. So our final expression is tau wall equals eta times u infinity divided by delta. This is the key result of the video. Now let us interpret it physically. The wall shear stress depends inversely on the boundary layer thickness. If delta is small, then the velocity changes very rapidly over a short distance. That means the gradient is large, and the wall shear stress is large. If delta is large, then the velocity changes more gradually. The gradient is smaller, and the wall shear stress becomes smaller. So we can summarize this in one sentence. A thin boundary layer produces a large wall shear stress. A thick boundary layer produces a smaller wall shear stress. This also tells us what happens along the plate. As we move downstream, the boundary layer grows. That means delta increases. So the wall shear stress decreases. In other words, the wall shear stress is largest near the leading edge and becomes smaller farther downstream. That is an important physical trend in laminar boundary layers. Of course, this linear velocity profile is only a first approximation. Real boundary layers do not have perfectly straight velocity profiles. In reality, the profile is curved. But this simple model already teaches us the essential idea. Wall shear stress comes directly from the velocity gradient at the wall, and that gradient is controlled by the boundary layer thickness. So today we learned three important things. First, how to model a boundary layer using an assumed velocity profile. Second, how to compute the velocity gradient. And third, how to determine the wall shear stress. In the next video, we will improve this model and use a more realistic polynomial velocity profile. That will bring us one step closer to solving full boundary layer problems with the von Karman integral method.